In this video, we'll see how to solve optimization problems. As with all of my videos, if you want to skip ahead to the examples, there will be links to the times of those in the description down below. So first off, what is optimization? Well, optimization is in general trying to find the best, whatever that means, possible outcome. Now, the best possible outcomes we're going to consider in this class are in this video are either sort of largest, as in sort of areas, volumes, profit, or smallest, as in costs, time needed. So we'll try to somehow find the best by finding a maximum or a minimum of a function. The function we're going to deal with is called the objective function. And that is just the function we are trying, not trying to maximize or minimize. And here's the process we're going to go through. So the steps to solve these problems. First thing, I'm going to try to write the objective function. Second thing, I'm going to try to rewrite in terms of one variable only. And this right here is the part that is most difficult, is actually reducing that. The third thing, once I've rewritten that, then I'm going to maximize or minimize, whichever one's called for, and get our answer. So let's look at some examples. First example is a very abstract example, and I guess before I jump in, I should realize this should not be a minimum, but actually be a maximum. I'll explain why as we get into the problem. And so, given y equals negative 3x plus 5, I want to find the maximum value of x, y. Well, the thing I'm trying to maximize, the objective function, in terms of the variables x and y, is just x times y. But as we are looking at single variable calculus where the functions are defined on one variable, I am not going to deal with this x and this y. When you take Calc 3 in college, you'll deal with some things where you can't get rid of one of these variables and then do partial derivatives and find a maximum or a sort of a local maximum or local minimum from that. But for now, we're going to try to write this in terms of one variable. And I notice y is equal to negative 3x plus 5, so I can just rewrite this as the objective function just in terms of x by replacing the y with negative 3x plus 5. And now I can just do my maximization or minimization that we learned a while ago. I have videos up on that already. By distributing the x, negative 3x squared plus 5x, and then taking the derivative, setting it equal to 0 to find the critical points. So 0 is equal to negative 6x plus 5. Subtract 5, divide by negative 6, and x will equal positive 5/6. And now I have a couple of options. So one option is I can take this information and plug it back in here to find y, and so I'll show that. So negative 3 multiplied by 5/6 plus 5. And negative 3 times 5 is negative 15 divided by 6 gives me negative 5 halves. And negative 5 halves plus 5 is equal to positive 5 halves. And from that, I can go ahead and say, okay, if x is 5/6, y is 5 halves, the largest possible x times y will be 5/6 times 5/2, which is, of course, 25/12. Now, I told you there's a second option. Here's the second option. Notice in the problem, it didn't say I needed to find y explicitly. It just said find the maximum value. So I could have alternately found x, plugged it into my objective function, either this one or this one. I'll show this one, or I'll walk through it. So 5/6 squared is 25/36, times negative 3 is negative 25/12, plus 25/6 gets me same answer. So I can skip a little bit of writing, I guess, if I just go straight ahead and put this into the objective function in terms of x only, but that is completely unnecessary. Second example. You have 400 yards of fencing to enclose 3 sides of a rectangular field. The fourth has an existing wall. What is the largest area that you can enclose, and what dimensions allow you to achieve this area? So in here, what we have is we have some type of wall already in place, and we want to enclose the other 3 sides to, put in a farm field, fence off a yard, something. I want to maximize the area, so the area of a rectangle will just be length times width. So area in terms of length and width is length times width. Similar problem here. I don't want to deal with 2 variables in here, 2 independent variables. I want to just deal with 1 so I can do my calculus maximization. But I'm not told in the problem what connects L and W. But here's the idea. So if I want to maximize this area, that means I should use all of the fencing. That means the perimeter of this fenced region, these 3 sides, should be 400. So L plus 2W should equal 400. And I'm going to solve this for L. So L equals 400 minus 2W. So I can substitute this back into here and get rid of L. So A in terms of W only will be 400 minus 2W times W. And now I continue just like we did last time. I'll distribute through the W and get 400W minus 2W squared. I know this is a parabola with a negative leading coefficient, so it opens downward. So we will have a maximum value. That'll be my maximum area. And so I take the derivative. A prime of W will be 400 minus 4W. Set equal to 0. 0 equals 400 minus 4W. Subtract 400, divide by negative 4. W equals 100. So each of these widths are 100 yards. And the length that we're left over with, either I see that length is 400 minus 2W, which is 400 minus 200, gives me 200 yards of length. Or I could just think of the perimeter, so I have 100 yards used, there are 200 yards left over. And so the maximum area will equal length times width. 200 yards times 100 yards, which will of course be, I have a plus there, that should be an equals 20,000 square yards. All right. Final example. I'm planning to cut four squares from the corners of a 9-inch by 12-inch sheet of cardstock. Afterward, I'm going to fold this up into an open box. What's the maximum volume of this box, and how large should the square that you cut out of each corner be? So the idea is this. I have a sheet of cardstock. I'm going to cut out these corners and fold along here to make myself this box with sides, but it's open. It does not have a top to the box. And in here, the volume, we're trying to maximize volume. The volume function in terms of length, width, and height of this box are, of course, length times width times height. But these are 3 variables. I want it in terms of 1 variable. So how do we do that? Well, we know that this is a 12-inch by 9-inch, so 9 by 12-inch sheet of cardstock. I'll mark each of these pieces as H. This here will be L. This here will be W. And so I know that this 12-inch side is made up of 1 L plus 2 H's. So L plus 2H equals 12. And I'm going to solve that for L. So L equals 12 minus 2H. I can do similar work for this 9-inch side. So W plus 2H, because I'm cutting off these squares that are H by H. W plus 2H equals 9. So W equals 9 minus 2H. And so that means I can simplify this down, or get this rewritten in terms of just H. So V in terms of H will be the length, which was 12 minus 2H, times the width, which was 9 minus 2H, times the height, which is still just H. And I can expand this out, so I'll put it in standard form at the same time. Negative 2H times negative 2H is 4H squared, times H is 4H cubed. Negative 2H times 9 is negative 18H. Negative 2H times 12 is negative 24H. Negative 18 minus 24 gives me negative 42. I have an H times another H, that's going to be H squared. Let me double check that to make sure I'm right. Yes, I am. Okay. And then I have 12 times 9 is 108, times H is 108H. All right, from here, I'm going to take the derivative to try to maximize this. So V prime of H is going to be 12H squared minus 84H plus 108. In here, I'm going to set equal to 0, so 0 equals 12H squared minus 84H plus 108. The first thing I'm going to try to do is simplify this down a little bit. So let's see. I can definitely divide everything by 4. So I'll divide out of 4 and get 0 equals 3H squared minus 21H plus, that divided by 4 gives me 25, 26, 27. And good news, I can divide this by 12 as well. So let me see, did I mess up something? Nope, that looks good. All right, so I can divide this through by 12, by 3, so I'll end up with H squared minus, so 0 equals H squared minus 7H plus 9. So, because 12 times H squared is 12H squared, 12 times negative 7 is negative 84, and 12 times 9 is 108. And now I need to solve this. And unfortunately, when I double check, I can check to see if this factors by looking at b squared minus 4ac. If this is a perfect square, this factors. If it's not, it doesn't. In here, b squared, so negative 7 squared is 49, minus 4 times 1 times 9, so it's going to be minus 36. And that gives me 13. Okay, so it does not factor for me. So let me flip to a new slide. I have some room to work. 0 equals h squared minus 7h plus 9. So I'm going to have to do the quadratic formula if I want to avoid the calculator on this. So in here, h equals negative b plus or minus the square root of b squared minus 4ac all over 2a. So negative b, that's negative 7, that's 7, plus or minus the square root of, we already did b squared minus 4ac, that's 13, all over 2. And so I'll get 7 minus root 13 over 2, and 7 plus root 13 over 2. I'll flip over to the calculator to get some approximates for that. So 7 minus the square root of 13 divided by 2 is approximately 1.69722. And the other one, 7 plus square root of 13 over 2 is approximately 5.30278. And so, if I'm not going to go to a graphing calculator, the question you should be asking yourself now is, which one do I use? Here's how we know. Here's what happens. So, I'm cutting out these squares, and I'm cutting them from both corners of each side. In here, the smaller side is 9. So, the largest square I can possibly cut out is 4.5 inches. Because if I go beyond 4.5 inches, I'll cut off more than this entire side of 9, because that would be 4.5 cut off here and 4.5 cut off there. So, really, the domain I'm considering from actually cutting squares out and actually folding up a box is h has to be somewhere between 0 and 4.5. That means that the critical point I'm going to consider is actually this one right here. And to finish it off, I'm just going to plug that back into the volume function. So let me do that. So we had 7 minus root 13 over 2. And in the volume function, let me try to remember. So I'll do the original one. We had 12 minus 2 times the height, so 2 times that answer, times 9 minus 2 times that answer, times that answer, and I get a volume of approximately 81.872 cubic inches. And I get that by cutting squares that are 1.697 inch on each side. Okay, before I move on, or before I finish this off, let's look at the graph briefly. So in here, if I were to graph it, I'm going to put in the original volume function when I got rid of all the other variables. Because if I somehow messed up in reducing it, this will show me. So 12 minus 2x times 9 minus 2x times x. I'll press graph. It's not going to be very useful yet. Okay. Now, I know that my maximum volume is 81, so I definitely need to change the window to make the maximum output bigger. So I'll go up to 100. And now you can see this. And you might be wondering, well, hold on. I want a maximum volume. Isn't the volume larger here? But what actually happens is when the size of the square gets so large, algebraically, the length and width will both end up being negative, which would multiply together to give me a positive. So I only consider from 0 to 4.5, this first little hump here. And let's just double check and see where that maximum is. It had better be these, or else I messed up somewhere. I don't really want to go back and change it. So maximum, I'm on the curve that I want. I'm going to get close to my maximum, but be on the left of it. I'm going to get close to my maximum, but be on the right of it. So I'm to the right of the maximum. And I'm going to get as close as I can to the maximum. Press enter. And I get 1.697 and 81.872. We got it right. Alright, feel free to comment below if you do have any questions. I hope this helped out.